Today we're going to talk about Parkinson's disease, but we're going to look at it a little differently, not just as a medical condition, but as the story of a really delicate chemical balancing act that's happening inside our brains, and what happens when that balance gets thrown way off.
I mean, think about it for a second. Walking across a room, signing your name, just standing still. For most of us, we don't even have to think about it. It's just automatic. But for millions of people, these simple, everyday actions become huge challenges. And that's really the central mystery of Parkinson's we're going to unravel today. So, what does this struggle actually look like? Well, it usually shows up in four main ways. First, you've got tremors, especially when the hands are just resting. Then there's rigidity, which is this intense stiffness in your arms and legs. You'll also see something called bradykinesia, which is really just a noticeable slowness of movement. And finally, postural instability, which makes keeping your balance incredibly difficult. These are the clues, the symptoms we need to understand.
Okay, so to get to the bottom of those symptoms, we have to go right to the source, the command center for our entire body, the brain. And specifically, we need to look at the two major systems it uses to control every single move you make. Think of it like this. Your brain has two systems for movement. You've got the pyramidal system, which is basically the go signal. It's the part that says, hey, let's go pick up that coffee mug. It starts the action. But then you have the extrapyramidal system, and this is the smooth operator. Its job is to control the quality of that movement, making sure your hand is steady, that you lift the cup smoothly, and that you don't lose your balance while doing it.
So, that pyramidal system, it's like a direct, non-stop highway from your brain's cortex straight down to your spinal cord. It sends that clear, voluntary command to move. It's all about the intention to do something. And here's the key. In Parkinson's, this highway is mostly fine. The go signal is still there. The problem is in the quality control department. And that quality control department? That's the extrapyramidal system. This whole network is about refining our movements, handling all the fine-tuning, our posture, our balance. And it's right here, inside this system, that things start to go wrong in Parkinson's disease. This is basically the scene of the crime. So you have to ask, right? If this system is the smooth operator, what's its secret? What's the magic ingredient that lets it fine-tune all of our actions so perfectly? Well, the answer comes down to a really delicate balance between two powerful brain chemicals. First up, we have dopamine. Now, you've probably heard of dopamine in other contexts, but here, in the motor system, it's the master refiner. It is the crucial signal that allows our movements to be smooth, controlled, and purposeful. You can think of it as the oil that keeps the engine running without any hitches. And on the other side of the scale, we have acetylcholine. Its job is totally different. It's the one that tells your muscles to contract, to tense up, to get ready to work. Now, both of these are absolutely essential, but they have to be working together in perfect harmony. And in a healthy brain, that's exactly what you see. This is beautiful, delicate balance. The smoothing signals from dopamine perfectly cancel out the contracting signals from acetylcholine. This equilibrium is what gives us that fluid, easy, effortless movement we completely take for granted. But in Parkinson's disease, well, that critical balance is absolutely shattered. That chemical symphony just falls completely out of tune, and that's when all the problems begin. So here's how it all goes down. It's like a domino effect. First, for reasons we still don't fully understand, the special nerve cells, the neurons that produce dopamine in this system, start to die. As they die off, the dopamine levels in the brain just plummet. Now, with not enough dopamine to keep it in check, acetylcholine is left unopposed. It becomes dominant, overactive, and that leads to way too much muscle contraction, which is the direct cause of all those symptoms we talked about. And this chart really just lays it all out, doesn't it? You can draw a straight line from the chemical problem to what a person experiences. The super low dopamine means you lose that smooth control, which causes the poor balance and the slowness. And at the exact same time, the unopposed sky-high acetylcholine causes all that extra muscle contraction, which leads directly to the rigidity and the tremors. So this leads us to the most important question of all. If we know the scales are broken, is there anything we can do to tip them back in the right direction? And the answer is yes, but, and this is a really critical point, current treatments can't bring back those neurons that have been lost. That damage, at least for now, is permanent. So the goal of therapy isn't a cure. The goal is to perform a chemical rebalancing act. The best strategy we have right now is to focus on the dopamine side of that scale. The idea is, if we can boost the amount of available dopamine in the brain, we can help push back against that overactive acetylcholine and, hopefully, restore a more normal level of movement.
Now, that sounds pretty simple, right? Just give the patient more dopamine.
But it turns out the brain is like a fortress, and it has this amazing security system that creates a huge problem for us.
And that problem is something called the blood-brain barrier. You can think of it like a super selective bouncer for your brain. It lets good stuff in and keeps toxic stuff out. And while that's obviously great for keeping us alive, it unfortunately recognizes dopamine as something that's not allowed in. So you can't just take a dopamine pill or get an injection, it'll never reach its target.
So scientists had to get really clever. They came up with this brilliant workaround, a compound called levodopa, or L-dopa for short. L-dopa isn't dopamine, it's what's called a precursor. Think of it like a chemical Trojan horse. Because it's a different molecule, it can pass the bouncer, it can cross that blood-brain barrier. And once it's safely inside the brain, the neurons that are still healthy grab it and convert it into the dopamine the system is starving for. It's an incredible way to restore that critical balance.
When you really step back and look at it, what Parkinson's shows us is just how mind-bogglingly complex our simplest actions are. Every step we take, every little gesture, it's all thanks to this fragile, perfectly tuned chemical symphony playing out in our brains. Understanding this balance isn't just about understanding a disease. It's about having a new appreciation for the incredible biological machine that lets us move through the world every single day.